Hello everyone, welcome back to Nunley Math. I'm your host Aaron Nunley. Thank you so much for joining me here today as we begin our discussion of three-dimensional geometry. Three-dimensional geometry. And you'll notice from the title slide here, I've got a lot of big words going on today. Polyhedrons, prisms, pyramids, and other 3D figures. In my class, we've just finished our discussion of perimeter and area formulas. We've talked about what it means to be a two-dimensional figure, and we want to stretch that and grow that into this idea of three-dimensional figures. Unfortunately, today is going to involve a lot of definitions, making sure that we understand what a lot of terms mean so that when a teacher or someone in the real world uses a term like polyhedron, we know exactly what they're talking about. But if you pay attention till the end, the reward and the payoff at the end is I'm going to show you guys a very, very cool app that I've been using for years on my iPhone, but that I now can use on Windows as well. And I think you're going to really enjoy this. It's got some neat things that will be very, very helpful to you as a student of geometry. So let's go ahead and get rolling, get started. Now, I want to make sure we understand what it means when I say that something is three-dimensional. So I'm going to take you back to some very, very basic terms that you learned back in elementary school, and I want to make sure we fully understand what those mean and why we use them. For example, when we talk about three-dimensional figures, we talk about things that have length, we talk about things that have width, and we talk about things that have height. That's because in our world, there are three dimensions that exist. Now, if you want to go down a real deep rabbit hole of sci-fi thinking and real deep science, some people talk about a fourth dimension as being time and a fifth dimension as being something that's just completely beyond the scope of this lesson. But by and large, most people think of the world as existing in three dimensions. And when we go to interact with our world, a lot of times it's useful to be able to measure each of those three dimensions. So when we think about measuring something very early on in elementary school, we usually think about measuring in one dimension. For example, I might say that something has a length of 1 inch. That means if I start here and I go to here, that's a measure of 1 inch. Most of us are comfortable with that. Height can be measured the same way. We just turn and measure 1 inch in a different direction. And width, we usually think of as being the third direction. Now, I can't really draw width on here. You can see length goes left, right, height goes up and down, but width would actually come from the computer screen out towards your face. That's what would give something depth, having one to all three of those. It's very difficult to represent all three dimensions on a two-dimensional surface like your computer screen. So typically when we talk about the third dimension on a two-dimensional screen, we usually draw it at an angle kind of like you're seeing here. Notice that I'm measuring that in units or inches, or if we wanted to think more metric, we would measure one-dimensional figures using centimeters. Then later on in elementary school, we begin talking about two-dimensional figures, or measuring two dimensions at once. For example, if I were to talk about a two-dimensional figure that has both length and height, you might think of the length as being 1 inch to the right, and the height as being 1 inch up and down. Now, if I were to go ahead and connect those lines with a length here, a height, a length, and a height, you can see that I actually get a square. Whenever we're measuring our two-dimensional figures, we're talking about how many squares it takes to cover the surface of that two-dimensional object. So we would think of this as being 1 square inch. And there again, depending on how much you're zoomed in, how big your monitor is, it might actually be an inch. On my screen, it actually looks closer to 2 inches, but 1 inch seemed to make the most sense. I didn't want to draw this too small, so it'd be hard to see. Anyway, so two-dimensional figures, we typically think of covering with squares. That's actually the reason we put this little square here, is because we're actually measuring a square, or measuring with squares. If this was 1 inch this way and 1 inch this way, 1 times 1 gives me a total area of 1 square inch. Now, we use square units or square inches or square centimeters because we're literally covering things with squares. So when we get to three-dimensional figures, we typically would think of something as having length, having height, again length, and height, but then we think of it as also having a width. And when I connect those, you can see that what we get is a drawing of a cube, or in this case, a cubic inch. It's 1 inch by 1 inch by 1 inch. It's 1 inch in all 3 directions. Notice that when we talk about one-dimensional figures, we're talking about things that go only in one direction. Two-dimensional figures are things that go in 2 directions. But when we talk about 3-dimensional figures, we're saying, how can I measure all 3 of these directions at once? This idea of an inch cube says, well, if you want to measure how much space a 3-dimensional object takes up, you're going to have to see how many cubes it takes to fill that object. And so we use cubic inches, cubic units, cubic inches, or cubic centimeters. Now, in the real world, everything is 3-dimensional. We don't really have 2-dimensional objects. We do have things that approximate 2-dimensional objects. For example, my computer screen doesn't have much width. It does have length and it does have height, but it does have a tiny width. Even a piece of paper has a very, very tiny, tiny, tiny width. So even a sheet of paper is 3-dimensional. Usually we think of 2-dimensional objects as being imaginary. So if I wanted to cover a sheet of paper, or if I wanted to cover a wall, a flat surface, you could do that. Now, length and height are not the only 2 dimensions we could use. You could use length and width, or width and height, depending on which directions you're trying to measure. This often begs the question, what is a 0-dimensional figure? Because we said everything in reality is a 3-dimensional figure. We can kind of think about some objects that are 2-dimensional figures, and really we can think of 1-dimensional figures pretty easily. How long is the edge of a sheet of paper? How long is a piece of string? But when we talk about 0-dimensional figures, that tends to throw people for a loop just a little bit. Typically, we think of a 0-dimensional figure as just being a point in space. It indicates a location that we're thinking about. It doesn't have a length, it doesn't have a width, it doesn't have a height. It simply is a point on a map or on a plane or something like that. Is that helpful? So when we talk about 3-dimensional figures, we're looking at things that occupy 3-dimensional space, things that have to be measured as a length, a width, and a height all at the same time. For example, a sphere is a very, very common shape, one you should be awfully familiar with because it's the shape of the Earth, it's the shape of a ball, it's the shape of lots and lots of things you're going to encounter in real life, marbles, jawbreakers, gum, a lot of times in spherical shape. Notice that a sphere has a lot in common with circles. A circle says you have a center point and the edge is the same distance from that circle point no matter which direction you go. A sphere takes that same idea and says if you take that circle point and extend forward or out into 3-dimensional space, it's also going to be equidistant that direction. You have a hemisphere, which is just half of a sphere. We think of the northern hemisphere and the southern hemisphere of the Earth. We have cones. Cones are very common. You see them out in the road, traffic cones. You see them at the ice cream store with ice cream cones. Very, very common shape. We've got a hexagonal prism here. Notice that the top shape is a hexagon. And then you've got these rectangles around the side, and then you've got the bottom side is a hexagon. And here's a triangular prism. A little shout out to Toblerone for making their candy into triangular prism shapes. Notice you've got a triangle over here, you got a triangle over here, and then you've got the space in between. Okay, so these 3D shapes should be fairly familiar to you. Let me give you some formal definitions and we'll look at something cool. When we talk about polyhedrons, polyhedrons are 3D figures made entirely of polygons. Well, that begs the question, what's a polygon? A polygon is a closed 2-dimensional figure with straight sides connected at their endpoints. So when I'm thinking about polygons, a triangle is a polygon because it has 1, 2, 3 sides connected at its endpoints. A quadrilateral is a polygon with 4 sides. Notice 1, 2, 3, 4 sides. They only touch at the ends. You've got a pentagon, which is a 5-sided polygon. You've got an octagon that has 8 sides. Notice again, all the sides are straight. Notice that they're connected at their endpoints. And then you've got all kind of random polygons. Notice this polygon has, I don't even know how many sides this has, 3, 6, 9. This is a 12-sided polygon, so a dodecagon. We call it a concave polygon because if you notice all these, the points all point out, but this one has some points that point in. It's called concave. these are all referred to as being convex. I like to remember it because I think about it as caving in on itself. Get it? Caving in, concave. Anyway, here are some things that are not polygons. A circle is not a polygon because the sides are not straight. This shape here is not a polygon either. Not a polygon because it is not a closed figure. Notice you have an opening right here. And this is not a polygon either because the sides connect at a point other than their endpoint. The shape touches right here. So if it had come down and up and down, but had not met in the middle, it would have been a polygon. As it stands, this is actually two polygons that are connected here at their endpoint. So we take those polygons and we assemble them into polyhedron. Polyhedron are 3D figures made entirely of polygons. This is a hexagonal prism. This is a polyhedron because it's made up of hexagons, one on top, one on bottom, and rectangles. The triangular prism from earlier has a triangle, and then the other sides are rectangles. Both of these prisms are polyhedrons. Down at the bottom, we have a couple pyramids. You have a hexagonal pyramid because the base, 1, 2, 3, 4, 5, 6, the base is a hexagon, and all the other sides are triangles. You got a triangular pyramid because you've got a base that's a triangle, and then all the other sides are also triangles. The formal name for this is actually a tetrahedron. We'll mention that again later. But all of these would be polyhedrons because they're made up of polygons. These shapes over here on the right are not polyhedrons. A sphere is not made of polygons. It has this one outside that's just kind of curved on itself. You got a hemisphere. Notice that's a circle at the top. That's not a polygon. And then this flat curved shape on the outside, also not a polygon. And then you have a cone. A circle is not a polygon. Neither is this curved shape here. None of those are polygons. Now, what I'm going to do is I'm actually going to hop out of this slideshow in just a second. I'm going to go to an app that I picked up from shapes.learnteachexplore.com. This is a wonderful app for exploring polygons and polyhedrons and how they fit together. I do want to go through one more time, make sure we know what our terms are before we do that. And once we have that, we'll hop out there and make sure it makes sense. You'll remember on the previous slide, we said that I had some prisms, which were polyhedrons. I also had some pyramids, which were polyhedrons. I want to point out the big difference between those for you really quickly. A polyhedron with two parallel and congruent bases connected by rectangles is called a prism. A polyhedron with one base, by which it's named, connected to triangles that meet at an apex, little typo there, that meet an apex is called a pyramid. So prisms have two parallel bases of any polygon shape, and all the other sides are going to be rectangles. Pyramids, on the other hand, only have one base, and that can be any polygon, and all the other sides are going to be triangles. Now, a lot of people have trouble distinguishing between those, so to help us, we're going to spend some time looking at the net of some three-dimensional figures. The net is just a two-dimensional representation of what a figure looks like when it is unfolded. So I'm going to hop out of this slideshow real quick. I'm going to hop over to this app. This is called Shapes. Shapes, and I did give you the website for how you could access this. Notice that when you open Shapes, you have several different three-dimensional figures listed. You can see it started me on pyramids. This is prisms. You can notice that we've got some more unusual shapes here. These are called solids of revolution. We'll talk about those in a little bit. And then you've got some really cool shapes over here. We'll talk about it at a later point in time. I want to start us off looking at various types of prisms real quick, because as you can see across the bottom here, there are lots and lots and lots of different types of prisms. But you'll remember from our definition, we said that a prism always has two polygon bases connected by rectangles. Two polygon bases connected by rectangles. So let's take a look at this one. This is the hexagonal prism. Hexagonal prism. I know it's a hexagonal prism because if I look at the top, and I'm going to go ahead and color this red. If I look at the top, you can see that the top base is a hexagon, and the bottom base is also a hexagon. That's what makes this a hexagonal prism. I have two bases. They are the same shape, they are the same size, and they are parallel to one another. And then if I spin this around, you can actually see that all the other sides are going to be rectangles. Now, this is very cool. If I go all the way over here to the right, I can actually unfold this into a net or a flat two-dimensional figure so that you can see the two hexagons and all the rectangles together more easily. Notice, by the way, when you unfold the shape, look at all those little rectangles. Notice they fit together to form a larger rectangle. That's actually going to be extremely helpful for us when we begin talking about surface area. So keep that in mind. I like this program because it allows me to fold and unfold and partially fold this shape over and over again so that we can get a good look at it. Here again, hexagonal prism has a hexagon on top, hexagon on bottom. They're both the same size, they are parallel, and they are connected by rectangles. By the way, this is not the only net that can be folded or that can be used to build a hexagonal prism. Any one of these will also work. This is actually really cool. I can fold this up. It's just a matter of where you decide to cut it or split it. But notice, even if I cut it or split it this way, it's still two hexagons connected by rectangles. You want to do one more of those? Let's pick a different one. That one's kind of cool looking. Let's look at that one. This is the net. Once again, you can see I can fold it together. Fold it together. And see if I can spin it. There we go. And it does make that hexagonal prism. Let me hop out of here real quick. So the hexagonal prism is just one of the many types of prisms we can look at. Here's a pentagonal prism. Pentagonal because, there we go. Pentagonal because if you look at the top base is a pentagon. If you were to look at the bottom base is also a pentagon. And if I were to spin it around, all the other sides are rectangles. In fact, you can see that if I open it up. Notice pentagon, pentagon, and then 5 rectangular sides. What else we got back here? Let's find another one. Here we go. Back here. Let's go. Oh, this is a fun one. Let's go to this. Let's go to this trapezoidal prism. Notice the top base is a trapezoid. The bottom base is a trapezoid. And if I were to open this up so you could see it, all those other sides are all going to be rectangles. And that really is the key to finding if something's a prism or not. Look to see if you have two matching bases that are connected by rectangles. You can do one more? Let's see, what else we got in here? Here's a triangular prism. Triangular prism. Notice the top is a triangle, the bottom is a triangle, and all the other sides are rectangles. It's important to point out that sometimes prisms will have rectangles that are all the same size. Sometimes they'll have sides that are different sizes. So you want to make sure you're looking out for that. I'm having trouble spinning this. There we go. Got it. Okay. Again, there are lots of different nets that we can use. I do also like this app because I can print these as well, which is very, very cool. Here's another triangular prism. Notice this is a right triangular prism because the top base is a right triangle and the bottom is the same. Again, all the other sides are rectangles. And I can unfold this so you can see it. Pretty cool, right? Now, I'm going to go back out of here. You'll notice, by the way, that we do have a cube as well. A cube is a special type of prism. Notice as a square on top, a square on bottom, and all the other sides are squares too. It provides us some cool opportunities to explore, but we're not going to do that today. Here we've got a pyramid on the other hand. Notice that this pyramid is called a quadrilateral pyramid because the base is a quadrilateral. In fact, it looks to me like this base happens to be a rectangle. So you could call this a rectangular pyramid. It might actually also be a square. If we had measurements, we could know that for sure. And we could call it a square pyramid. But you'll notice there's only one square. All the other sides are triangles. So when I go to unfold this into its net, you have one square base, and then all the other sides are triangles. If I were to fold it back up, notice that those triangles all connect to each of the edges, and they all slant so that they meet at a point here at the top. This point is called the apex. And just like with the prisms, I can take any one of these. This is a hexagonal pyramid. If I flip it upside down so you can see it, you can see that the base is a hexagon, and all the other sides are triangles. All the other sides are triangles. And I can unfold this, and you can see the triangles. Again, there are lots of different versions of this. I'm going to go to this one. This one's the most common one you're most likely to see. If I fold it this way, you can see you've got the six-sided base, the hexagon, and you have six triangles. Let's see. Pentagonals here. Again, five-sided base. Five-sided base. And then when I unfold it, you can see that there are also the five triangles. I am going to go ahead and move on just a little bit. I hope that gives you a big idea of the difference between those. Again, I always look for two things. Look for the shape of the base and look for how many bases it has. Pyramids always have one, triangles for the rest. Prisms always have two, rectangles for the rest. Now I am going to go ahead and point out to you that a cylinder is not a prism or a pyramid, but it does have a lot of characteristics in common with a prism because it does have two bases that are the same. Whoa. You'll notice that I can't color those separately though because this is not considered to be a polyhedron, so each shape is not getting colored by itself. But you can notice that the top and the bottom are both the same shape, just like in a prism. And you'll notice that it is connected by one large rectangle. One large rectangle. We'll talk a little bit more about that when we talk about surface area. A sphere. Notice that if I try and unfold it, it's made up of a lot of really cool little shapes as well. And I might as well go ahead and do the cone for you too. Here's the cone. Let's unfold that, see what it looks like. Notice you have a circle at the bottom, and then you've got part of a circle wrapped around to make the other side. Again, this is not a polyhedron. I said it's not a polyhedron because the base is not a polygon, neither is the flat surface. Also keep in mind that it's not a prism, but it's also not a pyramid. I will go ahead and tell you that cones do have a lot in common with pyramids, and so often we talk about them together, but it is not a pyramid. Last thing I want to make sure that we do before we go, this side is very cool because it also gives us what's called the Platonic solids. The Platonic solids are the 5 shapes that you can make by repeating a polygon over and over again, a single polygon. So, for example, this is a dodecahedron. You'll notice that there are 5 sides. So this is made entirely of pentagons. A dodecahedron has 12 pentagons. 12. Do meaning 2, deca meaning 10. So I can actually unfold that. You can see the 12 pentagons. Dodecahedron. We've already talked about cubes. We've already talked about triangular pyramids. I told you the more formal name for that is a tetrahedron. I told you we would mention that again. This is cool. This is an icosahedron. Icosahedron. It's made entirely of triangles. Triangles. In fact, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I think there's 18, but I lost count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 15, 16, 17, 18, 19, 20. That makes more sense. Icosahedrons have 20 triangles. And is that all of them? I think I got all of them. Let me look one more time. Oh yeah, this is cool. This is an octahedron. Octa, of course, meaning 8. It's built from 8 triangles. Now these are the only shapes you can make, the only polyhedron that you can make where you're exclusively using a single polygon, but there are lots of other shapes that you can make by mixing and matching. For example, if you think of a soccer ball is really just pentagons and hexagons stitched together. But yeah, these were actually thought to represent the parts of the universe. So if that's of interest to you, you can study that and with some ancient Greek history. But it's actually really got a cool narrative behind it. Not something we don't really have time for here today. What I am going to do is I'm going to hop out of this program again. That was from shapes.learnteachexplore.com. Very, very useful tool. One of my favorite tools. Thanks to them for allowing us to use that. One last time, polyhedron, 2 parallel congruent bases connected by rectangles. Pyramids are polyhedrons with 1 base connected to triangles that meet at an apex. And we can look at the net or unfolded 2-dimensional figure to see what it looks like. Now, I did go ahead and add this slide with those definitions again, as well as some pictures so you can familiarize yourselves with them. I will point out to you that one of the most common mistakes that people make is they often confuse triangular prisms for triangular pyramids, or sometimes even for rectangular pyramids, because it does have that triangle shape and it does kind of look like it goes sort of to a point at the top. But keep in mind, this is 2 triangles connected by 1, 2, 3 rectangles. Anytime you've got 2 triangles and 3 rectangles, you're going to know it's a prism. And then last, I did put pictures of those Platonic solids for you, just because I think that's kind of cool, and it might be something interesting for you to explore on your own. There again, I hope you enjoyed that. Thank you so much for taking the time to watch here with us today. As always, make sure that you like and subscribe. Make sure you smash that notification bell so that you can follow along anytime we add something new. We will take this information, we'll use it as we begin to explore surface area and volume in the coming lessons. Thank you guys very much. You take care of yourselves, all right? Bye-bye.